Hi, the topic this week is reliability, validity, and norms. This is information that you're going to need to complete the critique assignment that's due in a few weeks. The assignment is going to ask you to rate the technical adequacy of a test that you have chosen, one of the three that we talked about in the introductory lecture. So this week, you will learn about the terminology associated with technical adequacy, and that is reliability, validity, and norms. So let's talk a little bit about what is reliability and validity. Well, reliability and validity, first of all, are questions of quality. They help us determine whether the test is a good test or not, whether it's reliable, we'll talk, and in that sense that it gives us scores that we can depend on, and whether it's valid. In other words, it tests things that we are looking to test. It helps us aid in determining test accuracy and dependability. Reliability is easier to document than validity. You only need to show consistency of test scores, not goodness. So let me give you an example. If you have a car that didn't start today because the battery was dead, and you don't do anything to fix the battery, the car tomorrow is not going to start either. And unless you fix it, day after day when you go out to try to start it, it's not going to start. Now that is not a good car, certainly, because it's not taking you where you need to go, but it is a reliable car. It's reliable in the sense that you can depend on it. You know what's going to happen time after time after time. So it's easier to document whether or not something is going to be the same time after time, but it's harder to document validity because validity requires the test author to establish a relationship between the test and some real quality, such as a student's skill or ability in a certain area. And some of these qualities are hard to define. So, for example, how would you define cognition? Well, that's tough because we really don't know exactly what that is. We only know some of the things it might look like. So getting a valid measure of that is very tough. Even a valid measure of academic performance can be tough to achieve because what we're trying to do is to draw a link between what the student can do in school and what the test is measuring, and those links aren't always clear. Many tests provide us with consistent scores, but many scores are of limited use because of the question of validity. What are they good for? So think of validity as goodness. Instruments that we use, particularly for the purposes of assessment in special education and assessment for eligibility in particular, should have both properties. They should be both reliable and valid, but they may have only one. And in that case, it's not that strong of an instrument, and it is not an instrument that we should be choosing to use. So when we think about reliability and validity, we really are thinking about, if I look at the reliability and validity of a test and it's not good or it's not high, is this a test I really want to use to make important educational decisions about a child? And for my money, I want a test that's reliable and valid. And just to finish up, a measure can be reliable and not valid, just like that car wouldn't start reliably, but it's not a good car. But you can't have validity without reliability. A test can't be good unless it is also reliable. Now, in order to understand both the question of reliability and validity, you have to understand something about correlations. You can breathe a little sigh of relief because we're not going to be using a formula to compute correlations, because test makers do that for us and report to us the correlations that help us determine whether a test is reliable or not and whether a test is valid or not. So correlations are represented by that R, and I've used XX as a subscript. X is representing scores. So we think about correlations as the relationship between two scores or two variables, two sets of something. It could be two administrations of the same test, and that's something that we would be talking about in terms of reliability, or it could be the administration of equivalent forms or equivalent tests, two tests that purport to measure the same things, for example, and that might be something that we would talk about if we were talking about measures of validity. So we're looking at how do these two things go together. And if you were thinking about correlations in terms of what constitutes good tests, then we want to be thinking about relationships that are strong. In other words, things that go together very well. And correlation coefficients have ranges of from plus 1.00 to minus 1.00. It can't go, correlations don't go beyond 1. 1 is perfect. So we can have anything from 0.00 to 0.10 to 0.40 to 0.80, etc., all the way up to 1 in both a positive or a negative direction. A perfect positive correlation, it would be a plus 1.00. And that suggests that two things are going together absolutely perfectly. So if we were thinking of two administrations of the same test, the closer we would get to positive 1.00, the better, the more reliable a test would be. Negative correlations, on the other hand, are also things that go together very well, but they go together in the opposite direction, and those are represented by all the way up to a negative 1.00, and it can go from a 0.00 to a negative 1, negative 0.10, negative 0.40, negative 0.80, and so forth. That represents a negative correlation. But a negative correlation can be perfect. It could be negative 1.00, which is an absolute correlation of the negative kind. And just to further illustrate what's positive and what's negative, a positive correlation suggests that the scores go together in the same kind of way. When a score on one thing rises, the score on the other thing rises as well. So if I were to give two tests, for example, I would look for the relationship between those two tests by looking at, if you score high on one test, do you also score high on the other? And so if you score low on one test, you also score low on the other. So I'm expecting that scores will rise accordingly. High scores predict high scores, low scores predict low scores, and everything in between. That's a positive correlation. A perfect negative correlation, on the other hand, is scores that go together but in a different kind of way. A high score on one thing predicts a low score on another thing. And so rather than rising in a positive direction, the scores will go in a negative direction, such that a high score predicts a low score on another measure, and a low score on a measure predicts a high score on another measure. In terms of correlation, we can also have absolutely no correlation, and that way there's no relationship between the two items or the two tests or the two forms or whatever it is that we're trying to put together. So, for example, there's really not a correlation between your shoe size and your cognitive ability. There's no relationship between those two. So if you have big feet, you don't necessarily have a large IQ. It could be either way. That would be no correlation. Numbers closer to a positive or a negative 1.0 represent stronger relationships, and the greater degree of the relationship, the more reliable an instrument is. And that would also be true for validity. And we'll see how we look for that relationship in validity. But the higher the score, and in the case of looking at technical adequacy of tests, we want scores to go in a positive direction, so that the higher, the closer to 1.00, positive 1.00, the better. And remember, the plus and minus doesn't indicate the strength of the correlation. It simply indicates which direction it's going in. Here's a picture of that represents what correlations look like. Correlations can be plotted like we plotted last week. We did graphs of test scores. Correlations can be plotted on something called a scattergram, which gives us a graphic representation of a data set and shows the correlation. So on this slide, you can see that, that the dots on the scattergram approximate a straight line. And the nearer you are to a straight line, the closer you are to a perfect correlation. And in this case, we're looking at the relationship between math ability and grade level achievement. Let's say grade level achievement in math. So on the one hand, if I measure your innate math ability or somehow your cognition about math, if you will, and I look at how you do in math in school, I should see a relationship between those two things. And that's what this particular scattergram shows. It represents a positive correlation between two measures. So just to review types of correlations, we can have a positive correlation, and that is variables with a positive relationship that move in the same direction, low to low, high to high. And the scores on those variables will increase simultaneously. The closer to a perfect line, the better. A negative correlation is high scores on one variable associated with low scores on another variable. And then no correlation is when data from two variables are not associated or have no relationship. So there's no linear direction. And if you think about the scattergram, that would suggest that the dots are all over the place. There's no possibility of approaching a straight line. So now let's, if you understand correlations, we can start to understand reliability. And reliability is really the major consideration in evaluating the psychometric characteristics of a test, because you can't have anything else without reliability. You have to have reliability first. So the first thing that we look for when we evaluate technical adequacy is how reliable is this test. And when you get the technical manual of the test that you'll be critiquing, one of the first things I want you to look for is the section on reliability. And with the 3 tests that we'll be looking at this semester, that's going to be a fairly big section. There's going to be a lot of information presented. So part of my purpose here is to help you understand how to sift through that information and get down to the stuff that's important. If a test is reliable and the tested behavior is stable, a person will receive the same score on repeated testing with that test. Now, repeated testing, it doesn't mean that we wouldn't expect your score to rise between this year and next year. We certainly would. But remember that we also convert the scores to standard scores, and standard scores are comparable. So that we can compare this year to next year and see whether there's been a change in where you fall on the bell-shaped curve. So I'd expect a higher score on the test, but I wouldn't necessarily expect a significant difference in where you fall in performance on the bell-shaped curve, unless I'm a really good teacher, I hope so, and or you've changed or something significant has happened. That would create a difference in where you fell on the bell-shaped curve. But all things being equal, you're likely to be relatively stable in that year after year, although your test score, your raw score, will change. But repeated testing, when we talk about reliability, refers to repeated testing within short periods of time. So in other words, if my midterm is reliable, for example, I would expect that the score you get on the midterm today, if you were to take it today, would be the same as the score you would get on the midterm next week if you were to take it next week. That there's not going to be a significant change in what you know that enables you to answer the questions on the test, given a week or so in between testing. That would suggest that my test was reliable, and therefore the information I'm gathering about your performance on that particular test is reliable as well. I can count on it. I can use it to say something about you. Now, here's something really important for you to keep in mind, and it's going to be helpful for you when you are evaluating the technical adequacy of your test. How reliable is it? Well, we look for a certain level of score in order to say that a test is reliable. The reliability scores need to be at least 0.60 if it's a group test. So group tests are tests that are administered to a group of people all at once. So the standards-based assessment that we give to all students in certain grades are group tests. They're given in a classroom. Everybody takes a test at the same time. The level of reliability for those tests needs to be at least 0.60. So a relationship in terms of reliability, but not a super strong relationship. So it won't be a perfect straight line. There'll be scores around it, but in general, you would expect that as a high scoring groups are going to continue to score high, low scoring groups are going to continue to score low, with some fluctuation in the test. And we're going to be talking about how that fluctuation occurs in a moment. And then if we look at individually administered tests, each of the 3 tests that we're looking at this semester are individually administered tests. They have to report reliability coefficients of at least 0.85 or better in order to be considered reliable. So the first thing we do when we open the technical manual is to take a look at reliability. And the question would be, well, am I seeing reliability coefficients of at least 0.85? And if not, if they're lower than that, I begin to question how usable this test is to make statements about a person. To the extent that a person's score fluctuates randomly, the test lacks reliability. And I've given you the example here of a stretchable ruler versus a wooden one. If you want to measure how big a room is, for example, you don't want a ruler that's like a rubber band because you're going to stretch it differently each time you try to measure. It has flexibility, and so it's not giving you a reliable measure. It should be somewhat the same, depending on how stretchable the ruler is, but there's going to be variations in the number that you get. Versus a wooden ruler, which doesn't stretch, it's going to give you the same result every time. So I'm going to ask you to pause here and take a look at the retest worksheet that you have as one of the downloads for today. It's an exercise for you to work through. It's talking about a test called the Occupational Attitude Survey and Interest Schedule. So look for that, and it says test retest at the top. It's exercise 3. Okay, it says exercise 3. So please pause the tape right now and take a look to read and work through the test retest worksheet. Okay, you finished with that? I'm going to ask you this now. After reading that worksheet, do you understand a little bit about how reliability is reported? I've told you that reliability for an individually administered test should be at 0.85 or better. And so in your opinion, after looking at the information that's reported about the reliability of the Occupational Aptitude Survey, what do you think? Is that a reliable test? Are the reliability coefficients 0.85 or above for that test? Well, if you look at that particular exercise, you'll see that they've reported reliability information in several different ways. They're not just giving you one sentence that says the reliability for this test is 0.85 or 0.90 or whatever. They're breaking down reliability coefficients in a number of different ways. So they give us several tables that talk about the reliability of the test. And those tables are broken down by gender. So there's reliability for male versus female. They're broken down by grade level, so there's reliability for different grades who would take the tests, and it's also broken down by sub parts of the test. So you get a lot of different reliability scores. And for the big test that you'll be taking a look at for your assignment, there's even more tables than that. They're likely to be pages and pages of tables, and that could be overwhelming. But what I want you to look for when you're doing the critique is to look for the overall reliability score of the test. That will be reported. And remember, you're looking for 0.85 or better. And then take a look at how is it broken down. Once they break it out into subgroups, do they break it out by gender? Do they break it out by grade level? Do they break it out by ages? Do they break it out by subtests? So you may see multiple tables representing things like age and grade and gender and subtests and so on, and other ways of breaking it out. So I want you to say that, to look at that and tell me in the critique how it's broken down. So what kind of groups did they break it down into? And then simply, what was the range of reliability scores? So the range being, what's the lowest reliability score that's reported, and what area is that reported in? And then what is the highest reliability score reported, and what kinds of areas receive that high reliability score? That's it. So when you do your reliability review for the critique, it's probably a paragraph or two, despite the fact that there may be pages and pages and pages of reliability charts for you to look at. So it's a lot to sift through, but a limited amount of information to report. And then, of course, what's your opinion? And your opinion should be based on that number, 0.85 or better. And you may find that the test itself is reliable, but there are subparts of the test, whether it's for particular subtests, or whether it's for particular ages, or whether it's ages by subtest, that are less reliable than others. So I want you to think about that in your opinion and report on that when you're writing your critique. Let's talk about how reliability can be measured. This is something that can bog you down when you're looking at a technical manual as well. I don't so much care that you understand the mathematical formulas that compute reliability, so I'm not going to talk about that at all. But I do care that you understand that there are several different ways that reliability can be measured. The first and most common way is test-retest reliability. And when we think about correlations, that's pretty simple to understand. So we take a test and we give it to a sample group of students. Remember, test makers develop their tests using a sample group of students. So we take the test, we give it to a large sample, hopefully across different ages and grades and so forth, and we get the scores of those individuals on that test, time one. So our y-axis, our vertical axis, would represent scores on the test time one. And then we wait a couple of weeks, usually not more than 2, maybe 3. We wait 2 or 3 weeks and we give that same group the test again. And so it's the same exact test, same group of students, and our horizontal axis would represent the test scores time 2. And then various formulas are used to calculate how those scores correlate. And if it's a reliable test, wouldn't you expect people to get similar scores the first time they took the test as they do the second time they took the test, because there's only a short period of time in between. They don't have a lot of time to learn something new. There's enough time in between the two tests to allow them to forget about everything that was on the first test. I don't mean forget the information, because that's information they should have, but I mean forget the actual questions. So you probably won't remember the actual questions on the midterm 2 or 3 weeks after taking it. You may remember some, but maybe you'll remember the ones that you missed, but you won't remember all of them. So there's not really a learning of the test that can take place. So we have test-retest reliability. We correlate the two sets of scores. Another way to test reliability is through alternate forms reliability. We take 2 forms of the same test, and you will see some of the tests that we use, some of the tests that you all will be critiquing have a form A and a form B, or a Form 1 and a Form 2. They're essentially the same test, um, but the items are different on Form A versus Form B. They're different, but they're the same in the sense that they test the same skill and the same level of ability. Just to give you an example, if I were to design a test that was looking at your vocabulary knowledge, and the idea of the test was to have you point to the picture of a word that I give you. So I might put 4 pictures on a page, and let's say there's a horse, a dog, a cat, and a goat, and I ask you to point to the picture of the cat on Form A of my test. So that's a certain level of ability. It's a short word, it's a common word, and so I would expect probably your basic 3-year-old would know what a cat is. And then I have Form B of the same test. Well, on Form B, I might even use the same pictures, but instead of asking you to point to the cat, I might ask you to point to the dog. A similar level of difficulty, similar kind of skill, same size word, and also as likely to be seen in a typical household or community as a cat would be. And so essentially they're the same. So the test has 2 different forms, and I give half of my sample group one form, Form A, and the other half gets the other form, Form B. So remember, I've taken care to make sure that the 2 forms are essentially the same, just different items. And I correlate the scores. So on my y-axis, my vertical axis, I'm going to get the scores from the sample who got the first half, or Form A of the test. And then my horizontal axis is going to represent the group that got Form B. And I expect that their scores will go together. Maybe not as much as if it's the same group on test retest, but if they're the same kind of tests and my groups are similar, they've been well matched, then I should get fairly similar scores. Low performing individuals will get low scores regardless of the form that's used, and high performing individuals will get high scores regardless of the form that's used, even though there'll be a little variation. It won't be perfect. And I can also do split half reliability, which is almost like it's another form of alternate forms reliability, but it's more scientifically derived. I take all the items on a test and I analyze them internally. I give them to a sample group and I divide the test in half based on the results of that first sample's answers. So I look for questions that had the same amount of distinction amongst people in the group. So not necessarily the same skill, not necessarily the same kind of item like cat versus dog. It might be math versus reading. Well, that's a little far-fetched, but it's not the same skill necessarily. But the question distinguished amongst the sample in the same kinds of ways. So for example, if my sample had 50 students and question 2 was answered by 35 students, and question 4 was answered by 35 students, regardless of what skills they were measuring, question 2 and question 4 are considered to be similar because they distinguish within the group in the same kind of way. So I put question 2 on a new test, and I put question 4 on another test. In other words, I divide the test in half based on what's called internal consistency, based on performance of the first sample. And then I take my divided test. Now I've got 2 halves of my test, and I give it to 2 new groups, and I correlate their responses with group 1 getting 1 half of the test, and group 2 getting the other half of the test, and correlating their scores. That's split half reliability. It's a little more complicated than that, but that's the simplest way to describe it. And then, so test retest uses the same test. Alternate forms and split half reliability use different forms of a test, whether it's forms that have been developed one way to create forms that are usable for the test, or whether we take one test and just simply split it in half. Now, just one last thing about alternative forms reliability. Alternate forms reliability is useful because when we have a Form A and a Form B of the same test, we can use that test more often. As a general rule of thumb, major standardized tests of things like achievement or cognition can only be used once a year because we don't want students to get used to the items on the test. So when we have a test that has already created two forms of the same test, Form A and Form B, we can use that test every 6 months or so because it is essentially looking for the same information, but it's giving the student a totally new way or totally new item to get that information about. So that creates more usable tests when there's two forms. And the final way we're going to talk about of reliability is inter-rater reliability. And that's the consistency of test scores across examiners. So if we have a test that requires some subjective interpretations, so writing tests are a good example of that. If I'm going to score how grammatically correct your sentence was and how good your sentence, complex your sentence is, let's say, I may differ from how I score an individual's written sentence from how you might score that same individual's written sentence. I might be looking for certain aspects of grammar to be correct. You might be looking for other aspects of the sentence to be correct. I might think that a 5-word sentence is better than a 4-word sentence. You might just look at the quality of that sentence. So there will be some differences in how we score an answer. So when there are items that can be scored differently by different examiners, there's not an absolute answer, then we want to look at the consistency of scores across examiners. How closely do you and I score the same test? Another example that's probably a little bit easier to understand would be if I give you short answer questions on my midterm versus multiple choice questions. Well, multiple choice questions, there's usually only one answer. It's either A, B, C, or D. Short answer questions, you might answer in a couple of different ways. And I might look at those answers and say, okay, well, those fit what we've talked about in class. But another person might look at it and say, well, that doesn't really make that much sense to me. So we would want to look at whether or not the test was reliable in terms of how two different people would rate the test. So we correlate the scoring of two different examiners to get inter-rater reliability. Let's finish up with this. What affects reliability? Well, a number of factors can affect the reliability of the test. One is test length. Longer tests are better than shorter tests because there's more items to get information about a person on. So that information is likely to be more reliable. And you may have taken tests in the past that kind of ask you the same question, but ask it in several different places and kind of a little bit differently each time. That's an example of trying to get at the reliability of your answers. And obviously that needs to be a longer test. One question alone wouldn't really get at that same information. And then another thing affecting reliability would be the test-retest interval. So we would want to have just the right amount of time in between the two test times if we're doing test-retest reliability. I think I mentioned already 2 to 3 weeks is usually ideal, much more than that, and we're getting both maturity, students will have learned more in the meantime, as well as other things that will creep into affecting your score. And if it's too short of a time period, if only a week goes by, for example, you may remember more of the test than you would if a couple of weeks had gone by. Another thing affecting reliability is guessing. So, for example, a true-false test tends to be less reliable than a multiple choice test because with true-false you got a 50-50 chance of being right even if you don't really know the answers. Take that test again and you still don't know the answer, you're not going to remember whether you put true or false down or not. You still have a 50-50 chance of getting it right, so there's a lot of room for error. versus multiple choice, where there's 4 questions. It's a 1 in 4 chance of getting it right. Chances are that's going to be a little bit more reliable. And then finally, that's really important to think about are variations in the test situation, whether it's in the examiner or the examinee. So if I'm using retest reliability, for example, and I give the sample test first in a large auditorium where everyone has one of those individual flip desks in their seat, where they're taking the test, versus the next time I give the test, which is in a very large classroom where everyone has their own desk, which is separated from other people's desks by walking space. What do you think would happen? Which test are you likely to get? Some more cheating or more peeking on other people's answers in the first situation versus in the second situation where there's a greater space between? And then what about if one room, the first time, let's say it's 90 degrees outside and the first room isn't air conditioned, versus the second time you come to take the test and you're in an air conditioned environment? That's likely to contribute to some variations in scores. So just the environment, and then the examiner. I might get a very friendly examiner who's giving out hints about what the answers are versus an examiner that's not giving any hints. I might get someone who takes the time to establish rapport, and that's going to make me try harder, versus someone who's very gruff and is obviously rushing through the test, in which case I'm going to rush through it too. So that kind of thing can affect reliability. And then finally, what I bring as the examinee to the test situation is going to affect reliability as well. Did I have breakfast this morning? Did I have a fight with my significant other? Is it morning when I'm more awake, or is it afternoon when I've already had a long day and I'm likely to be tired, and so forth? So things about me can affect how reliable the scores are. I might get an answer right today because, boy, it was morning, I'm right on, I had a cup of coffee, I'm ready to go, versus, oh, it's late in the afternoon, I've worked all day, just want to take this test and get it over with, so I'm going to rush through it. My answers are not going to be as truly representative of me as they might be otherwise. And we're going to talk about something that tests give us, which is called standard error of measurement, which helps us determine how much fluctuation there's likely to be in a test based on the notion of how much error is there in a test. So let's look at standard error of measurement. The basic assumption of assessment is that error exists. Remember that. Error exists. There is error present in every assessment that we do and in every test we give. There's error present in our observations. We can make judgments that are incorrect. There's error present in interviews. We can ask questions and interpret them differently. There's error present in the tests themselves, true, false versus multiple choice, ambiguity of the question, and so forth. Error is there, and I bring error into the test situation, as I was saying, how awake I am, how comfortable I am, and so forth. That all contributes to error. So we have internal error, which is error in the test itself, problems in the test itself that contribute to fluctuation of scores. And then we have external error, which is problems in the environment or the examiner or the examinee that contributes to fluctuations in scores that affect reliability. So we know that error is there. We can't control for external error too much, although we should try to. And one of the things we'll be talking about next week is how we set up test situations in order to minimize external error in the assessor, the environment, or the examinee. But test makers try to control for the error that's internal, the error that's present in the test itself. And they do it in a number of different kinds of ways. We already looked at how they try to control for bias, which is a form of error. But another thing they do is is mathematical calculations that help determine how much internal error is actually in the test. So they're looking for variables that affect scores that are internal to the test, not the ones that are external. When we look internally, we're looking at variation that is called error and is the standard error of measurement, the SEM. And that's an important thing to talk about. Instruments with a small standard error of measurement are preferred over instruments with a large standard error of measurement. So when you're looking at technical adequacy, you might want to look for how the test maker reports the standard error of measurement. And keep in mind, throughout your history now, from now on, in terms of giving assessments and scoring them, a single test does not accurately reflect what is known as a person's true score. Any score has two parts. True score, what is really true about the student's ability, and error. Error is random. It can inflate or deflate a score. But error, remember, exists and it's part of every score that we get. So if I have, for example, a standard score of 100 on a Q-based test, what would that be? 100 is the mean. So that would be the mean score. I could say with some certainty that my performance on that test was average. But if I factor error in to the test, the standard error of measurement, I'm going to have to understand that that's only an estimated true score. It's not a true score per se. It's not an absolute score. I have to take error into account and understand that it affects my score both in a negative direction and in a positive direction, so that my true score is somewhere around that score of 100, but it's not necessarily that score of 100 by itself. Error is present, so the question is how much does my score fluctuate around the score I received today? And what we talk about now today in terms of test scores is that range of scores, or something called a confidence interval. And that's a very important term. And we're going to get to how it's applied also. So calculating the standard error of measurement, how do test makers do that? And how could you, if the test isn't reporting standard error of measure, how could you calculate the standard error of measure and apply it to the person's score to calculate a range of scores? Well, here's the formula for standard error of measurement. Standard error of measurement is equal to the standard deviation of the test times the square root of, there's that symbol, square root, the square root of 1 minus the reliability coefficient. So there's that RXX. Standard deviation times the square root of 1 minus the reliability coefficient. And it's based on the normal distribution theory because it's using the concept of reliability and standard deviation to compute the error that is in a test, the internal error. And computing that standard error of measurement helps us get to a confidence interval. A confidence interval is the range of scores for an obtained score, plus or minus the standard error of measurement. We're going to do some work that will hopefully illustrate what that means. So just remember this. A confidence interval, many tests report a confidence interval. If you look at the Woodcock-Johnson printouts, for example, they give you a number of different scores. They'll report Q scores, they'll report Z scores, they'll report percentile ranks, they'll give you age and grade equivalents, but they also have a column that says CI, or confidence interval, and most tests today do that. And a confidence interval is the range of scores around an obtained score. So you'll see, let's say, take that score of 100, that might be the Q score that's reported, but the confidence interval might be 95 to 105. So that's a range that is including the standard error of measurement. And what that's saying is that somewhere between 95 and 105 would be this person's true score. We don't know what it is absolutely, but we know that it's somewhere in that range. And that's what we like to talk about today, because it recognizes that there is error in every test. We can't count on a score as being 100% reliable. So you have a worksheet, and the worksheet is called Worksheet 1, Standard Error of Measurement. It's called, and it gives you the formula at the top, the standard deviation times the square root of 1 minus the reliability coefficient. And this particular worksheet shows you how the range of error can affect the range of a student's score based on the amount of error that's in the test. So I want you to read and work through, first of all, before we do the worksheet, I want you to pause the video again and read and work through the exercise 21, which is on standard error of measurement. It's a reading that you have. I'd like you to read that and work through the questions. And then when you're finished, come back and we will talk about how we construct confidence intervals at certain levels of confidence before we move on to complete this worksheet that you have, standard error of measurement. Okay, so did you read through that exercise? If you did, you should be able to answer these two questions, and you should be beginning to understand confidence interval a little bit better. The first question is, how do you construct a confidence interval at 68% confidence? So if you read through that exercise, it's talking about the p-body, and it's telling you that the p-body is measuring confidence intervals at 68% by factoring in the standard error of measurement for various subtests or slices of the reliability of the test, based on the notion that 68% confidence is using the standard error of measurement and adding it to the obtained score and subtracting it from the obtained score one time. So if you had a score of 100, again, a Q score of 100 on the p-body, and you knew that the standard error of measurement for someone your age and gender was 5, you would know that to be 68% confident that we had captured your true score somewhere, that the range around that score that you obtained, that score of 100, would be from 95 to 105. Because 68% confidence, I'm adding and subtracting the standard error of measurement from your obtained score of 100. Now, 68% confident means that I'm pretty confident that that score is really your true score, but I'm not 100% confident. I'm 68% confident, which means that I'm also 32% confident that your score isn't anywhere between 95 and 105, that it's somewhere outside that range. Well, that's okay if I'm doing a spelling test that I'm not going to use to put you in special education. But think about this. If you're going to use that test as one of the tests that helps determine whether a person is eligible for special education or not, how confident do you want to be? I want to be more confident than that. And so we can have a range of confidence anywhere from 40% to 99%. We never get 100% confidence. But the two numbers that are most commonly used in testing are 68% confidence Again, I'm not too happy about that, but as long as it's not for eligibility, I'm okay. Or 95% confidence, which I'm happier with if it's for eligibility. So now, having read that exercise 21, do you know how to construct a confidence interval at 95% confidence? And if your answer to that is that you add and subtract the standard error of measurement 2 times, then you read that exercise correctly and you understand something about confidence intervals. So now we'll take your score of 100 and we'll say that the reliability coefficient, the standard error of measurement that we're working with is 5 for your age and gender and so forth. So at 68%, we add and subtracted 5, because that's 1 SEM. But for 95%, we're going to add and subtract 10, because that's 2 SEM. That's the SEM 2 times. So to be 95% confident about your score of 100, I would subtract 10, giving me 90, and I would add 10, giving me 110, and I can say I'm 95% confident that your true score, your real ability on this particular test, is somewhere between 90 and 110. So it's a bigger range. So the more confident you want to be, the bigger the range is around your obtained score. Now that can be significant. Let's say that your score on the test was 90, and again we'll work with the SEM of 5. So to be 68% confident, the range around that score of 90 would be 85 to 95. Well, again, remember the bell-shaped curve, and it's a Q test. 85 is 1 standard deviation below the mean. 95 is moving us pretty close to the mean, but I can say with 68% confidence that your obtained score represents a true score for you somewhere between 85 and 95. So it's in the average range. It's at the lower end of the average range, but it's certainly well within the average range. I'm 68% confident of that. But now if I want to be more confident, if it's an eligibility decision, I construct a confidence interval at 95%, and I see that the range in which your true score is likely to fall is now somewhere between 80 and 100. Now 80 places you more than 1 standard deviation below the mean. It places you in the low average range or the below average range. So I can say with 95% confidence that your score on the test is either in the low average range or in the average range or somewhere in between. I like that less. I'm more confident that I found your true score, but I certainly like that less in terms of making decisions about who you are and whether you're eligible for special education or not. On the one hand, you might be, on the other hand, maybe not. So confidence intervals are useful in that they help us see that error is present in the test. They help us account for that error, and rather than relying on a single score, they give us a range to think about. And that range may help us determine that a student either needs to be retested with a better test, or maybe we can't say something about the child based on that test alone, which we already know that we shouldn't be doing. So now I'm going to ask you to take a look at your worksheet, and let's complete the worksheet starting with question number 1. And question number 1 says, a test has a reliability estimate of 0.75. Find the standard error of measurement if the standard deviation of the test is 5, or if it's 10, or if it's 25. So what you're going to do is 3 calculations. The first calculation, it would read 5 times the square root of 1 minus 0.75. That's the numbers that we plug into the formula. The standard deviation is 5, and the reliability coefficient is 0.75. And it's going to stay the same for, the reliability coefficient is going to stay the same for all three problems. Then we're going to do another calculation using 10 as a standard deviation. So it will be 10 times the square root of 1 minus 0.75. And then finally, it'll be 25 times the square root of 1 minus 0.75. So you go ahead and do those calculations. So the answers to question number 1 would be, we're looking at the SEM for standard deviation of 5 would be 2.5. For a standard deviation of 10, it would be 5. And for a standard deviation of 25, it would be 12.5. That would be our standard error of measure. Did you get that? Let's move on to question number 2, which is essentially the same kind of question. And this time the test has a reliability estimate of 0.64. So it should say 0.64. Remember that it can't be more than 1. So in any of these worksheets, if you were talking about reliability and you see a decimal point missing, put it in. Those dots are always hard for me to make sure are there. But so it's 0.64. Find the SEM if the standard deviation is 5, 10, or 25. So take a moment to calculate that. Ready? So for question number 2, the answers are 3, 6, and 15. Now let's move to a slightly different kind of problem, which is question number 3. This time we're going to keep the standard deviation the same. We're still going to do 3 calculations. We're going to change the reliability coefficient. So the first problem will look like this. It will be 15 times the square root of 1 minus 0.96. So you can go ahead and do that. Then the second one will be 15, because standard deviation stays the same, times the square root of 1 minus 0.83. And then finally, it will be 15 times the square root of 1 minus 0.36. So go ahead and do those calculations. And once you've completed that, your answers for question number 3 should be 6, or I'm sorry, 3 would be the first answer, 6.5, and then 12. That should be your answers for that. And then question 4 is the same kind of question, but this time the standard deviation is 50, and the reliability estimates are 0.96, 0.83, and 0.36. So go ahead and do those. And your answers for that should be 10, 20.6, and 40. Now let's talk about question number 5. Examine the answers to the questions in the first 4 problems and pay attention to the relationship between the estimated reliability and the standard error of measurement. What is that relationship? What we should see is that, that as the reliability increases, the standard error of measurement goes down. And then the next question, looking at the relationship between the standard deviation of the test and the standard error of measurement. Think about that for a moment. And the relationship is, as the standard deviation goes up, so does the standard error of measurement. So the greater the standard deviation, the greater the SEM, the higher the reliability coefficient, the lower the SEM. Those are important relationships. We can see that both standard deviation and reliability affect standard error of measurement. You can see how important reliability is because it really has an effect, and you can almost predict a test is reliable if you know the standard error of measurement. It should be low, less than 5 as a general rule, because much more than that, and we're getting far too much variation. So you can see that with the Peabody. If you worked through all of the questions, just looking at the charts, I'm going to challenge you. Take a standard score on the Peabody for a 8-year-old. Take a standard score of 90 and calculate a confidence interval at 68% for that score for that student, and also a confidence interval at 95% for that score for that student. You were asked to do this as you were working through the worksheet, but if you come up with some numbers of your own and work through this a little bit, you'll see that the relatively high standard error of measurement on that Peabody contributes to a very wide confidence interval for many of the scores, for many of the various age levels of students. So is the Peabody a good test to be using? Not necessarily for some students. Although it is a fairly reliable test, it also has a fairly large standard error of measurement. And Peabody is one of those tests that there's 4 possible answers to each question. And so it's more like multiple choice than anything else. So there is error there because you can guess. So there's fluctuation of scores, which contributes to the reliability level, and there you have it. You have a broader confidence interval. Now, I'm going to ask you finally to complete question number 7 on our worksheet, and that is the Swift spelling test has a mean of 28 and a standard deviation of 5 and a reliability coefficient of 0.64. What is the SEM? And then construct confidence intervals for a score of 17 on that test. So it's got a mean of 28. We're interested in a score of 17. And I want you to calculate the SEM, first of all, for that test, and then construct a confidence interval for a score of 17 at 68% confidence and at 95% confidence. So take a moment to go ahead and do that. Finished? Okay, so your answer should be that the standard error of measurement on this test is 3. And if I want to construct a confidence interval at 68%, my interval is going to range from a score of 14 to a score of 20 for that score of 17. And if I want to have 95% confidence, my interval is going to range from 11 to 23. And if you want to practice what we were doing last week, you could convert that raw score of 17 into a z-score and a percentile rank and a Q-score, let's say, and you can construct confidence intervals for all of those different kinds of scores on this test. Just a little more practice if you want to do it. Now let's talk about validity. Validity is a question of whether or not a test is actually measuring what it says it's measuring. And that sounds pretty simple. Does the test actually measure what it says it's measuring? And there are 3 types of validity measurements that we can consider. Is the content of the test representative of the content that we're interested in? So let's talk about content. If it's a reading assessment, for example, do the items on the test look like they represent what we consider to be reading challenges? So is the student basically asked to read in order to complete the items on the test? Reading would be one thing. Now, reading's a pretty broad term, so let's think about content. What kind of content would you expect on a reading test? Well, the first thing that comes to my mind is there should be vocabulary, word attack kinds of content. So the student might be asked to read a list of words. That's one kind of content that looks like reading to me. Another kind of content might be that students are asked to read a paragraph and answer questions about that paragraph. That's another kind of content that looks like reading to me. So those two things are representative of the content that I'm interested in, which is reading. The next kind of validity measure that we can talk about, we're going to spend more time on each of these. So I'm going to go through these relatively quickly on this slide. The second kind is criterion-related validity, and that asks the question, do the scores obtained on this test compare with other criteria representing the same trait? Well, that's a complicated way of saying, do these scores, if I give you this reading test, do the scores that you get on this reading test compare with how you do in school in reading? I would expect that there would be some relationship between your scores on a reading test and your performance with reading in school. I also might expect that if I compared your scores on this reading test to scores on another test that also tests reading, there should be some relationship between those two sets of scores. So that would be criterion related. There's a criteria that I'm expecting my test to compare to, whether it's performance or another test. And then finally, and this is the most difficult of the three, is construct validity. Does the content relate to a specific attribute or theoretical construct or characteristic? And that is, if I'm giving you a reading test, what theories would I have about how you should do in reading? So one theory that I would have would be that poor readers would do more poorly on a test than good readers would do. And so I would expect my test of reading to be able to differentiate between actual poor readers and actual good readers, because my theory is that poor reading goes together with poor performance. And so what else would dictate your performance on reading? What other theories could you have? Well, I would have a theory that perhaps third graders might do better than kindergartners on a reading test, because my theory is that as you go through grades of school, you get better and better at certain things. So I would expect that my test would actually differentiate between kindergartners and third graders. That's a construct. It's kind of based on a theory that I have about how this stuff works. So now we'll go through each of those three things a little bit more carefully. Does the content of the test represent the content you want to assess? Well, I just want to say that this area of validity is the one that you have the most say in. You should be able to look at any test of academic achievement especially and say, in looking at what's on this test, I think this test is really measuring what it says it's measuring. So again, you should have in your mind a picture of what kind of content looks like reading. You should have in your mind a picture of what kind of content looks like third grade math. You should have a picture in your mind about what kind of content represents middle school social studies. So looking at the test, you could look at the actual items on the test and you could answer the questions of content validity yourself based on the knowledge base you already have. And when test makers ask professionals to look at the content of a test and give opinions about validity, they look at three particular factors. They look at the appropriateness of the content. Does it look like a reading task? So reading a word list, for example, is very appropriate as a measure of reading. It's very appropriate content. But that's not enough. They also look at completeness of the items. So completeness of the items being, does it cover all of the various kinds of things that are represented in this skill called reading? And we often make mistakes about that because we assume that tests that we're getting scores on cover more than they actually do. So I'm giving the the Wide Range Achievement Test as an example. The Wide Range Achievement Test measures achievement in reading, math, and writing. It has One has now two reading subtests. One measures word recognition. It used to be the only subtest on the rat to measure reading, simply word recognition. And the complaint about that was that that's not complete. Being able to read a list of words doesn't necessarily get at phonemic awareness, doesn't necessarily get at phonics. I mean, they could all be sight words. It doesn't necessarily get at the vocabulary that you bring to the reading situation. It doesn't get at reading comprehension and so forth. And those are all aspects of reading. So even though a word list is appropriate, it's not a complete measure of reading. So in order for the test to be really valid, I want to see that it has more to it than just the word list. So the makers of Rat 3 went ahead, and when they revised the test from 2 to 3, they went ahead and they added a section for reading comprehension. Well, that's good. So it's more than what it was before, but their reading comprehension measure asks you to fill in a blank. It's a closure kind of measure. And I would argue that that's really not a complete measure of comprehension. So I still think that the rat is not, that has less validity in terms of its content, because although its content is appropriate, it's not complete. And then we also look finally at the format and response mode, and we think about this in terms of the students that we might be assessing. How are the items presented, and how does the examinee answer the items? So how are the items presented? So for example, a simple example would be that if the items are visual, if you need to look at a picture in order to identify a word and you have limited vision, that content's not valid for you. How are you asked to answer items? One example that I have, I was testing a very young child, and I was using the Peabody Picture Vocabulary Test to get a measure of his receptive vocabulary. And that is one of the tests that asks you to point to a picture, 4 pictures on a page, and you are given a word, and you are asked to point to the picture that represents the word. And the first picture, the first set of 4 pictures, the stimulus word was hand. And there were various items, one of which was a drawing of a hand. So I said to the child, point to the hand, because those are the directions on the test. I said, point to the hand. And the child raised his hand up and showed it to me. And I had to mark him wrong, because he didn't point to the hand. He knew what a hand was. He had that vocabulary, but he didn't have the vocabulary point. He didn't know what that meant. And he didn't have also certain test-taking behavior, which is understanding that people are asking you to do something that's somewhat abstract and something that they probably know the answer to, but you're being asked to show them that you know the answer. He didn't understand that either. So the way that he was being asked, the way the content was presented in which he had to respond, was not valid for that student. Again, even though he knew the content. So now take a moment, pause this, and read and work through the content validity worksheet, which is exercise 8. So take some time to read through that, and that will help illustrate different ways that test makers measure content validity. So ready? What is your opinion of the content validity of the TOEL 3, the test of written language? Do you think it's a valid measure of written language? First of all, is it appropriate? Does it look like a written language task? And I would say that it is appropriate. It is asking you to do something that is requiring you to demonstrate your knowledge of some aspect of language, written language. Write in a word, or write a sentence based on a word. Is it complete? I would say no. It's not a complete measure of written language. There's certainly a lot more that goes into written language than just what's presented in that test. And is the format and response mode appropriate in terms of the content? Well, that's a it depends kinds of answer. So you think about your students, and would that be an appropriate format, the way the items are presented? Is that something that you ask students to do, that you work with, or that you see students doing in the classrooms that you've seen? It should be a format that they understand. And then, is the way that they're being asked to respond appropriate for the students that you work with? So again, content is something that you probably know more about than even the test makers do, because you understand what kind of information is presented in the work that you do, how it's presented, what it looks like, and whether or not the students you work with would be able to respond to that format. Now let's move to criterion-related validity. And criterion-related validity, we're looking at comparing scores with some other criteria known to be an indicator of the same trait or skill. I talked about measuring your performance on a test to your performance in a classroom. That's one way to look at it. We could also look at it in terms of measuring your performance on a test of one thing. So let's say a test of reading, comparing that to another test of reading that's known to be valid. We can do it concurrently, so there's something called criterion-related concurrent validity, and that's doing it within a very short time frame, often the same day. So I might give you two tests on the same day, one test A of reading, and then test B of reading. So I'm trying to measure the validity of test A, and I correlate the scores that you get on test A to the scores that you get on test B the very same day, and there should be a strong relationship between those scores, assuming my test A, is a valid measure of the same kinds of things that test B is supposed to be a valid measure of. I could also look at your scores on test A and compare it to your performance today in school. So concurrent means within a very short time frame. And I can also look at it criterion-related predictive validity, which is looking at how well an instrument can predict your performance on some other variable. So I give you test A in reading, and I predict that you are going to be a good reader in the future. Okay, that you're going to get good grades in high school, for example. Or I give you a reading test and I predict that you're going to be good in content areas as you start to add content areas into your curriculum, because reading is so heavily linked to the content. If you can't read, you really can't do well in content area classes. So predicting that you'll do well down the road. So now take a moment and read through exercise 5, which is the concurrent validity worksheet. And you're looking at the reading and arithmetic indexes. And look at that and see how criterion-related validity is measured. So pause here to do that. So if you've read through that, what's your opinion of the concurrent validity of the reading and arithmetic indexes? With this worksheet, you get a chance to see how a form of criterion-related validity is measured. You're getting a chance to see what the technical manual that you'll be looking at looks like. So now, remember, you're going to be looking at reliability, and we talked about how to look for that. You're also going to be looking at validity. One way to look at it is you look at the content of the test and give some opinions about how you think the test is measuring certain things, whether you think the content is valid or not. But then you're also going to be looking at tables that report both criterion-related validity and construct validity. So criterion-related validity, if you look at exercise 5, is not as simple to talk about as reliability is. Reliability, we know that the correlation figures have to be 0.85 or better in order for the test to be considered reliable. But with reliability, if you noticed in the tables that were reporting validity, You were not seeing correlation scores that were high like that. Many of the correlations are 0.3, 0.4, some a little bit better, but they are low and even lower than what we would expect of reliability of a group test. And you may say, well, based on that, this is not a very valid measure. But the issue with validity is that we don't expect the same level of correlations when we're looking at criterion-related validity. So if I'm comparing test A with test B, which is a different test, but it's supposedly measuring the same things, I'm not going to get as high a relationship as if I were comparing the same test to itself. Because test A might be looking at the same kinds of skills as test B is, but it's not the same test. So I'm going to expect a lot of variations of scores, and they might be measuring the same thing in different ways, giving even more variation of scores. So there isn't an absolute number that enables us to determine whether a test has validity or not in terms of criterion-related correlations. We find correlations, but the values of these are lower than what we would be looking for if it was reliability. So how do you know if the values are high enough? I'll be honest with you, you can only tell because the test maker says that it is. And they give a p-value, and the p-value needs to be less than 0.05. So just remember that. And if the p-value is less than 0.05, they've done statistical calculations that tell them that the validity correlations they got were significant enough to be reportable, and that they suggest that their test is valid in terms of criteria related validity. You have to go by the test maker's statements. Now you'll see the tables, and again, I would like you to report the overall validity. Did they measure criterion-related validity? If so, was it concurrent or predictive? What were the overall correlation values for overall validity? And then again, did they break it down by age or grade or subject, subtests? If so, how? And then again, what was the range of validity correlations from lowest to highest? What kinds of things were the lowest? What kinds of things were the highest? Again, a couple of paragraphs about validity in terms of criterion-related validity. And finally, in terms of validity, we're going to look at construct validity. Construct validity describes a psychological trait, a personality trait, a psychological concept, attribute, or theoretical characteristic. That's what a construct is. So if you were thinking how to define construct, well, that's what it is. And a construct has to be clearly defined, even though it's an abstract concept. And the types of studies that we use to establish construct validity are we look for developmental changes, we look for correlations with other tests that represent that construct, we look at something called factor analysis, we look at internal consistency, which is item consistency, we look at convergent and discriminative validation, and we look at experimental interventions. Phew, that sounds like an awful lot. But first of all, the simplest thing when we think about construct validity is to remember that we have a theoretical or psychological concept or construct that we start out with. And we test our test, test A, we'll go back to test A. We test test A against those constructs, those characteristics, those concepts. So we have a set of beliefs about how this content of our test should change based on our theories. So developmental changes are a good example. I expect that students' scores would increase on a test as they grew. As they got older, their scores would get higher. And if that is the case, that is one measure of validity. And last week when we created a grade equivalent chart, if you'll remember the slope of that line went up. And in fact, average scores did increase across grade levels, which provides some measure of the validity of that instrument. That based on what we know about development, that scores should increase over time. Correlations with other tests. Now, one of the most common things that we do, so we talked with criterion-related validity about correlating my test A, which is a test of reading, with someone else's test B, which is also a test of reading. That's criterion-related validity. But let's say I have a test of reading, and I have a theory that reading and intelligence are linked. So in other words, the smarter you are, the better reader you are. Then I could correlate the results on my test of reading, test A, with an existing test of intelligence. And I would expect there would be some relationship between those scores, such that people who scored higher on the intelligence test would tend to score higher on the reading test, and vice versa. So those are correlations that I might report if I were reporting about construct validity. We're not going to talk about factor analysis and internal consistency and these other kinds of things because frankly the calculations are a little bit too difficult. Briefly, what we're looking at is how things fit together. So if I had an achievement test, for example, that was looking at reading, math, and writing, I would expect in doing some of these statistical analyses that items grouped together according to the category in which they fell, so that reading items would tend to group together and math items would tend to group together and so forth. So it's a simple way of explaining it. But I'm most concerned with, in terms of your understanding of construct validity, developmental changes and correlations with other tests. So now take a look at the construct validity worksheet, which is exercise 10. And read through that because I think it's an excellent example of construct validity and how it is measured. So it should give you some understanding of this admittedly tough concept. So pause here and take the time to read through that and work through the questions. Okay, so if you've done that, again, I said it was a really good example. The important thing is to start out with a theory, and the authors of the Comprehensive Receptive and Expressive Vocabulary Test had several theories. So did you pick up on that? They had several theories about language development. Number one, they thought it should be related to age, and that makes sense to me because what I know about language is the kids talk more and more the older they get. So your receptive vocabulary, what you understand, and your expressive vocabulary, what you're able to say, should increase over time. It should be related to age. The older you are, the better your vocabulary, receptively and expressively. And they tested that and they found that to be true. So that lent some validity to their test. Another theory they had was that receptive and expressive language should correlate, so that as your expressive language increased, that would be one axis, your receptive language vocabulary would increase as well, that there would be some relationship between those two sub-tests. And in fact, what we know about language development in general is that in typically developing children, expressive and receptive language go hand in hand, although receptive language is a little higher generally than expressive language. And if you've ever learned a second language, you know that to be true. You understood things far sooner than you could express things, but they still grow somewhat together. And that turned out to be true for these test authors. And then they thought that results should differentiate between groups. They thought that somehow the results would differentiate between typically developing individuals, individuals with learning disabilities, individuals with language disorders, and individuals with cognitive impairments, that they should fall into different scoring groups based on classification. And in fact, they found that to be true as well. So That's a really nice example of how construct validity is measured. Here's some of the issues associated with validity. Tests can be used inappropriately even if they are valid instruments, and results obtained can be used in an invalid manner. And let me give you an example of those two things somewhat go together. But there are tests that are valid for certain things that we overuse or use in different kinds of ways than what they should be used for. And the Peabody Picture Vocabulary Test is a good example of that. I think Peabody is a valid measure of your receptive vocabulary, with the confounding variable that you need to have a certain level of vision and you need to be able to interpret two-dimensional representations of sometimes very complex words. But other than that, it is trying to get at, do you understand what this word means, and can you pick out a picture that represents it? So it's a valid measure of receptive vocabulary. However, it's often used as a measure of intelligence, and I think that that's inappropriate because your vocabulary theoretically is a representation of your cognitive ability. It's one representation of your cognitive ability, but it's a very small representation of that. It doesn't include all the other kinds of content that I think would help make a measure of intelligence complete. And so to me, it's not valid for measuring intelligence because it lacks completeness. And it certainly, the form in which it's looking at your abilities is limited. So, and it requires you to point, which is not always good, as we've already said. So using that test and using the results of that test as a measure of intelligence invalidates the test results. It's an invalid usage of that test. So we have to be really careful that we use tests for what they're supposed to be used for. And even if a test maker tells us that they should be used for something else, we have to use our own judgment about that. Tests can be biased against or discriminate against different groups, and we've talked about that at length. If a test is biased against a group, or if items are biased against a group, then it's not a valid test for that group. And items can be biased, so the whole test itself could be biased, or particular items on a test could be answered incorrectly by one group versus another. And then predictive validity may predict accurately for one group and not another group. So again, that's bias. Bias has a heavy effect on validity, so it's important to look for that in tests as well. So to summarize validity, you are good judges of content. We can talk about concurrent or criterion related validity, which is comparing your test to something else that is a similar measure of the same thing, whether it's performance or another test. And then construct validity, which is all about theory. And you'll be using those three, should be reported in the technical manuals of the tests that you look at. And now finally, 2 more slides, I think. Or maybe 3, we're going to talk about norms. And norms are the statistics used to develop derived scores in norm reference testing. It comes from a normative sample. Those statistics come from a normative sample. Most norm reference tests have several samples. So they gather samples at different ages. These are people, samples are people, samples at different grades, and sometimes different samples for boys and for girls. So we know we get norms for various age groups, we get norms for various grades, and sometimes we get norms for boys and norms for girls. And sometimes even we can get norms for different populations, although not very often. So you could get norms for Caucasian students versus norms for African American students. They might be different. You could get norms for typically developing students versus norms for students who had a particular developmental disability like Down syndrome. That could be possible. But there's always something called a normative sample. And it's really important to know what that normative sample looks like. So when you look at your technical manual, you're also going to be looking at their normative sample, the sample of individuals on whom the test was developed. And the first thing that we think about, the most important word, is how representative of the group that we're interested in testing is that normative group. And so we think about representativeness in a number of different ways. Gender, so you want to see the test both boys and girls. Age, you want to see a test a wide range of ages, especially the age of the students that we're testing. We want to look at grades as a representation of students. If you're testing fifth graders, you want to see that fifth graders were included in the development of norms. Acculturation of parents. Who are the parents of these children? And we look at education, level of the parents, most often the mother, the female caregiver, is their educational status is looked at because mothers have traditionally been the primary caregivers of children, and so they have the most significant impact on children traditionally. It's not always true, but test makers tend to look at the educational level of the female caregiver. Occupation of the family. Now here they tend to look at the male caregiver, so sexism goes both ways, and the income level of the family can be important. All three things comprise socioeconomic status, and all three things are important to that. So income alone is not predictive, for example, of acculturation. They look for racial identity. So you want to see various races and ethnicities represented in the normative sample. We look for geography, so the various areas of the country, urban, suburban, and rural, community size, large versus small, and population trends. And we look at the intelligence levels of the normative population. Is it the whole bell-shaped curve, for example, or is it that middle of the bell-shaped curve only? What is represented in that normative group? And this is just a partial list. I'm sure if you sat down, you could probably generate a larger list than this. What groups would you want represented if you were choosing a test to use with the population with whom you work? Think about, who do you work with? How would you want to see them represented in terms of a normative group? And that's one way that you can evaluate a test in terms of its technical adequacy, to determine if your group that you work with was included in the development of norms. Now notice I haven't included much in terms of disability. Most tests don't include disability groups in their normative group. That's, I think, a problem. Makes the test useful for determining whether a person is not developing typically, but it doesn't make it useful for other things, I don't think. And we also, not only are the norms representative, but we also want to look at how recent that normative group was used, how recent are the norms. So one thing that test makers use to get a representative normative group is a census. And so we want to look to see if a census was used, because censuses tell us gender, age, grade, proportions of all of those things in the general population. We want to see that the norms were proportionally representative of the various groups that are found in a census, and we want to see that census was a recent census. More than 10 years old is too old. So if a test has a normative group that was based on a census that is more than 10 years old, it is not a good test to be using. Think about how much life has changed in the last 10 years. That means that what people know has changed also, and how they know it has changed. So those old rotary phones, or how about a phone booth? You might have seen that as little as 10 years ago, but you don't see it today. So that an item on a test that included something like that would not be valid anymore, and it wouldn't be representative of what people today understand. So we want to see all of the various age groups, grades, different incomes, different racial identities, and so forth, represented in the group on whom the test was normed, because those norms are what we will be comparing our students to when we give them that assessment. So I want you to look for that in the technical manual and report on what was represented. So what we want is the proper proportion of people. It should be the same as a population proportion, so we think about the census. We want to look for the number of subjects. It needs to be large enough to be stable and to represent small groups or characteristics like Native Americans. So a large enough sample that we would get a significant percentage of Native Americans in the sample as well, not just one or two. It has to be large enough to get a full range of derived scores, so scores across all ages or grade levels. It should be current. This says not older than 15 years. I use 10. Most tests are actually renormed every 10 years or so to represent today's individuals and the specific content on the test. And it should be updated. Not only should we use recent census, but we should also update the content of our test to reflect changes in what people know and understand. And when we update, they can use smaller samples to do that. So that finishes up what you need to know about technical adequacy to help you with your critique that's coming up in a little while, and also to help you evaluate tests that you might be using in the future. These are all things to think about. And hopefully, if you're ever on a panel that is selecting a test for a school to use, you'll be thinking about these things as well. So complete all those exercises, and you have a topical activity for this week as well. And next week we're going to not need the calculators anymore, because we're going to be talking about the basics of test administration. So we've talked about how tests should be constructed and what scores mean, and next we're going to be talking about how to use them. Okay?